Okay, so I'm going to prove the law of cosines, the next one. If triangle ABC has lengths A, B, and C, representing the length of the sides opposite of the angles with those measures A, B, and C, right? Capital A, little a is opposite of big A, little b is opposite of big B, and little c is opposite of big C. Then we know that c squared is equal to a squared plus b squared minus 2ab cosine c. So, of course, we have a cosine c in there, so I'd like to know what that is. But what I need to do first to be able to deal with cosine is I need a right triangle. So what I can do is from vertex B, I can, let me get that, I can draw an altitude, right? So this is altitude BD. So the first part of the proof, of course, proof, draw altitude BD. Now that I have my altitude, I can find cosine of C. So cosine of C, remember cosine is adjacent over hypotenuse. So cosine of C is just going to be CD over A, which implies that CD would be equal to, so if I solve for CD, that would be A cosine of C. Now, just like in the previous one, I'm interested in c squared, and I know using the Pythagorean theorem that c squared is equal to ad squared plus bd squared. So I'm not interested in cd, which is what I got using cosine of c. I'm actually interested in ad, but it's easy to find that ad given that cd, right? So ad is equal to the entire length, which is b, minus this piece here, cd. And of course, we know that instead of writing cd, I can write a cosine of c. So I know that AD is equal to b minus a cosine of c. Now, I'm going to try to find sine of c, so that way I can get my BD side for this right triangle, right? So I know sine of C is equal to, uh, so opposite BD over A, right? So this will be BD over A. And if I solve for BD, this will give me BD is equal to A sine of C. So now I have my AD and my BD. So by the Pythagorean theorem, I know that c squared, right? C squared is equal to AD squared plus BD squared. Okay, but now instead of using AD and BD, I can substitute these values, right? So this implies that c squared is equal to, so AD is the same thing as b minus a cosine c. And BD is the same as a sine of c. All right, so doing some more math, this implies that c squared is equal to, so b minus a cosine c squared is going to be b squared minus 2ab cosine of c plus a squared cosine squared of c. And then, oh, I need the squared here, right? That's bd squared. And a sine c squared is just going to be a squared sine squared c. Okay, so now this implies that c squared is equal to, so remember my formula that I want to prove, a squared plus b squared, right? I do have a squared and b squared, but a squared is attached to the cosine squared c, and a squared is attached to the sine squared c. But I know using the Pythagorean identity that I can do sine squared plus cosine squared is 1, and I would get that a squared all by itself. So I can rewrite this as a squared times sine squared c plus a squared cosine squared c plus b squared minus 2ab cosine of c. And then this will give me c squared is equal to a squared times sine squared c plus cosine squared c. Right, I factored out the a from both of those guys, plus b squared minus 2ab cosine of c. And then, to finish it off, I know this is just 1. So this implies, of course, the sine squared c plus cosine squared c is 1. So c squared is equal to a squared plus b squared minus 2ab cosine of c, which is exactly what I wanted to prove. I wanted to prove that c squared is equal to a squared plus b squared minus 2ab cosine c. So that is the proof.